Hi, my name is Kian Brown, a freshman and part of the Biomimetic controls group, specifically on hardware and fine motor control. So in terms of the design, we have a back-wheel drive using two DC motors with encoders on them in order to both track their orientation and their speed, and making sure it lines up with the speed that we get later on, something I'll go on in a little bit. It was cost effective and its weight was easy to deal with, allowing us to balance it with the propellers as well. The turning mechanism at the front using a digital servo was really easy to make as the wheels in the front were just controlled directly by the orientation of the servo. The interpretation of the data, turning acceleration into velocity, we have both our peripheral and our central sending acceleration and orientation data through the Arduino Nano's gyroscope to our peripheral, which will convert the difference in acceleration over multiple iterations into linear velocity for the motors. Programming the functions, we have discrete functions like changing from ground state to flying state, which was done with gyroscope data. Since it's sent through each iteration, it's really easy for the program to recognize the difference between that instead of adding a separate function between iterations that increase the delay between them and cause even more input lag. The limitations with this were slower, tedious updates. Registering user input was difficult throughout the entire thing, but we were able to get around this by creating functions that rely on the change in things like velocity and gyroscope data, and lost data, like button inputs get lost in between iterations because of the constant flow of information being deleted and being entered and deleted. Initial knowledge was also difficult to deal with because of the cost limitations of Arduino tutorials and the items that they require you to purchase. Moreover, physical connectivity, wiring, and microcontroller organization was difficult because of all the batteries necessary to power all the motors and encoders and the propellers as well. And wiring was difficult because of all the connections between the ESCs, items, and the motor drivers and such.
Hello, my name is Jonathan Ridley, and I'll be going over the communication sector of our biomimetic control project. Here's a little bit about me, a little bit about the Arduino RP2040, and here's what the project was about. The base of our project was communication, in which the Arduino offered two means of it, Wi-Fi and Bluetooth. We started out with Wi-Fi, but we abandoned it because of our lack of a way to find a direct communication between the two Arduinos that we had. One would act as a server and client. The code you're seeing now is for the server, still for the server, and there we go. So all that you just saw was for the server, and this is for the client. Now there is more to it, but because of a faulty save, the code got deleted, unfortunately. So with this, we switched to Bluetooth, which proves to be much more efficient because we could just send bytes to each Arduino. So we would send the IMU data from the central device to the peripheral device, but we would first approximate that data and then send specialized bytes off of that approximation to the peripheral device. So you see that here's the data range, and that based on the range, it's going to send a specified byte. So we see that it's 0.1 and 1, and then this classifier just tells the program whether it's on the X, Y, or Z axis. Here we have the approximation process. On the left side, we have the central device sending the data to the right side, which is the peripheral device. And here we have our spacing mechanism, which allows each byte to have an equal chance of being sent to the peripheral device and not overlooked. To wrap things up, our IMU data is gathered and approximated by the central device, to which bytes are then made for, and then the peripheral device gathers and interprets those bytes to then act on. Thank you.